A pristine gold surface exhibits a distinct yellow luster under neutral white light. It is one of the most recognizable optical signatures in human history. Yet, when placed next to typical elemental metals like aluminum, iron, or silver, gold is an obvious outlier. The vast majority of pure metals present a uniform silvery white appearance. That silvery look is the default optical response for a metal. It occurs because the atomic structure of these elements reflects all wavelengths of the visible spectrum with nearly equal efficiency. Gold behaves entirely differently. Its color is not the result of a surface pigment or a chemical tarnish, but a highly selective manipulation of electromagnetic radiation. The metal lattice itself actively filters the light striking it. Gold's appearance is a subtractive anomaly, created by removing very specific parts of the visible spectrum before the light reaches your eye. To trace exactly which parts are removed, we measure the incoming white light by its photon energy. The visible spectrum spans from approximately 1.8 electron volts at the red end up to 3.1 electron volts at the violet end. When this spectrum strikes gold, the lower energy red and yellow wavelengths, falling between 600 and 700 nanometers, are cleanly rejected. They bounce off the surface perfectly intact. However, the higher energy blue and violet light behaves completely differently. Photons carrying more than 2.4 electron volts of energy penetrate the surface and are permanently absorbed into the lattice. Because the metal traps the blue and violet photons, the light that bounces back is heavily biased toward the remaining red and yellow frequencies. Human vision processes this specific subtractive mixture as a warm golden yellow. In classical physics, a metal's interaction with light is explained by the Drude model. This treats the metal's outer conduction electrons as a continuous fluid, a gas of free electrons flowing loosely around a rigid grid of atomic cores. When an electromagnetic wave hits the metal, it forces these free electrons to oscillate. They shift rapidly to screen out the incoming electric field, and in doing so, they perfectly re-emit the photons outward as a reflection. This free electron mirror works up to a very specific limit, called the plasma frequency. Above this resonant threshold, the electrons simply cannot oscillate fast enough to keep up with the incoming light, and the metal abruptly becomes transparent. A common misconception assumes that gold is yellow simply because its collective plasma frequency happens to sit right in the middle of the visible spectrum, cutting off the blue light. This graph plots reflectance against photon energy. Gold's actual plasma frequency is 8.45 electron volts. This sits deep in the ultraviolet range, far outside the 1.8 to 3.1 electron volt window of human vision. Throughout the visible spectrum, gold's free electron reflectance is flat. Classical electrodynamics dictates that gold should be a perfect, featureless mirror. To explain why the blue light vanishes, we must abandon the classical free electron model and look at the discrete internal architecture of the atoms themselves. Quantum mechanics replaces the classical fluid of electrons with strict, localized energy bands. The critical boundary in any solid is the Fermi level. In gold, the inner 5D orbitals overlap to form a dense, tightly packed band of fully occupied energy states entirely below the Fermi level. Conversely, the diffuse outermost 6 sp orbitals form a broad conduction band spanning across the Fermi level, providing a massive network of empty, available energy states above it. When a photon carries exactly the right energy, it strikes a bound electron in the 5D band, violently promoting it into an empty conduction state. The electron leaps the gap, consuming the photon in an interband transition. In a solid gold crystal, the precise energy required to bridge the gap between the top of the 5D band and the available 6 sp states is exactly 2.4 electron volts. 2.4 electron volts is the exact quantum equivalent of blue-violet light. The color of a gold bar is the macroscopic sum of trillions of these individual quantum leaps, continuously deleting blue photons from the ambient light. This quantum architecture immediately introduces a paradox. Other noble metals possess nearly identical electron configurations, yet they do not absorb visible light. The physical appearance of gold is completely unique among the heavy transition metals. Look at its immediate neighbor on the periodic table. Silver sits directly above gold in group 11, sharing a homologous valence structure of a filled d shell beneath a single s electron. This chart compares their respective interband energy gaps. In solid silver, the gap from the 4d band to the conduction states requires nearly 4.0 electron volts. That places its absorption threshold deep in the ultraviolet region, leaving it to reflect all visible light uniformly as a white, silvery mirror. By comparison, gold's energy bands are severely crushed together, shrinking the gap down by an enormous 1.6 electron volts and dragging the absorption threshold directly into the visible spectrum. Standard quantum mechanics cannot explain a 1.6 electron volt collapse in the band structure. The equations accurately predict a silvery metal, but they completely fail to predict the yellow color. The missing variable lies deep in the core of the atom. Gold has an atomic number of 79. That massive cluster of 79 protons exerts an immense electrostatic pull on the electrons orbiting closest to the nucleus. To avoid collapsing into the core, the innermost 1s electrons are forced to orbit at extraordinary velocities, reaching approximately 58% of the speed of light. At 58% of the speed of light, classical approximations break down entirely. Einstein's theory of special relativity dictates that the mass and inertia of these electrons must sharply increase, triggering a cascade of structural changes throughout the entire atom. To understand a macroscopic piece of gold, we have to integrate the strict cosmic speed limit into the laws of quantum chemistry. We have to turn to the relativistic quantum mechanics of Paul Dirac and see exactly how a fundamental law of spacetime translates into the yellow sheen on a wedding ring. Looking at group 11, silver and gold appear as direct vertical neighbors. They share an identical valence structure, a completely filled inner d shell beneath a single s electron. Chemical intuition suggests that because of this, gold should simply be a heavier, denser version of silver. Based on that logic, polished gold would reflect all visible light uniformly, giving it a brilliant, featureless white luster. To explain why it doesn't, many rely on a simplified model where an electron makes a jump between the 5d and 6s orbitals of a single atom. But an isolated atomic transition like that violates quantum selection rules. It is physically impossible for a single gold atom to produce this color on its own. To find the source of that yellow hue, we have to move past the isolated atom and look at how electrons behave collectively within a solid crystal. In a bulk sample, gold atoms condense into a highly ordered three-dimensional grid called a face-centered cubic lattice. As the atoms lock into this grid, their electron clouds overlap. Their sharply defined energy levels are forced to broaden into continuous energy bands. The outermost s orbitals overlap aggressively with their neighbors, creating a broad, continuous conduction band that electrons can travel through freely. We call the boundary representing the highest occupied state at absolute zero the Fermi level. Because the conduction band straddles this Fermi level, there is a vast density of empty states immediately available for electrons to occupy. By contrast, the buried d orbitals overlap weakly. They form a dense, narrow cluster of filled states located entirely below that Fermi boundary. This creates the fundamental rule of metallic optics. The color we see depends on the specific energy gap between this filled d band and the empty states in the conduction band. We can use silver as the standard for how a normal noble metal interacts with light. In the delocalized conduction band, silver's electrons act like a plasma, shielding the interior by reflecting incoming electromagnetic waves. Silver's filled 4D-derived bands sit extremely deep, far below the empty conduction states. This creates an energy gap of roughly 3.8 to 4.0 electron volts. 4.0 electron volts is a high threshold. It places the energy required for a transition deep into the ultraviolet spectrum. Visible photons, red, green, and blue, simply lack the quantum energy to bridge that gap and trigger an absorption. Because no visible light is absorbed, the free electrons reflect the entire spectrum uniformly, giving silver its bright white appearance. When we switch to gold, we find the exact same structural layout, but the filled 5D bands are positioned much higher. Gold's band structure shows a distinct shift. The energy gap has narrowed significantly. That threshold drops down to approximately 2.2 to 2.4 electron volts. A 2.4 eV threshold corresponds exactly to the blue and violet wavelengths of visible light. Red and green photons still lack the energy to cross this gap, so they are reflected back to our eyes. But blue and violet photons carry enough energy to excite a 5D electron into the conduction band. Those photons are absorbed by the metal. Our eyes see what remains of the reflected spectrum, a mixture depleted of blue light, which we perceive as yellow. These transitions are not random jumps. They are mathematically precise events occurring in momentum space. We map this space using the Brillouin zone, a 3D map of all possible electron momenta in the lattice. A transition only occurs when a photon can match both the precise energy and the precise crystal momentum of an electron. However, an optical photon carries almost no physical momentum compared to the electrons inside the lattice. Because the change in momentum is virtually zero, the transition must be vertical. The electron moves straight up the energy axis. In gold, these vertical paths line up with that 2.4 electron-volt energy requirement near the highly symmetric X and L points of the zone. The color of a gold bar is the macroscopic result of these precise vertical transitions happening trillions of times a second. To calculate these energy band structures, physicists traditionally use the standard Schrödinger equation. For light elements like carbon or silicon, this non-relativistic framework is nearly perfect. But watch what happens if we were to apply those same non-relativistic rules to a heavy gold crystal. The calculation yields a broken model. The 5D band is pulled downward, and the conduction band is pushed up. The non-relativistic energy gap widens to roughly 3.7 electron volts. A 3.7 electron volt gap sits entirely in the ultraviolet, meaning visible light could no longer bridge it. Under the standard laws of quantum mechanics, gold will have no way to absorb blue light. It would look exactly like silver. The non-relativistic model fails because it misses a massive 1.6 eV redshift in the absorption edge. That missing variable completely changes the physical appearance of the metal. Without that massive redshift, gold would reflect the entire visible spectrum uniformly, completely losing its iconic yellow hue. Quantum mechanics gives us the bands and the optical transitions, but it provides the wrong energies for heavy atomic matter. To resolve this 1.6 eV discrepancy, we have to uncover a physical force powerful enough to warp the very geometry of the atomic orbitals. Correcting the true color of gold requires us to ultimately bridge quantum mechanics with Einstein's absolute cosmic speed limit.
Look at gold and silver. Sitting next to each other on the periodic table, these noble metals share nearly identical valence electron configurations, a filled D shell beneath a single S electron. If we apply standard non-relativistic quantum mechanics to model how light interacts with this structure, the equations predict that gold should behave exactly like a heavier, denser version of silver. It should reflect the entire visible spectrum uniformly, presenting a brilliant, featureless white luster. But it doesn't. Gold actively absorbs higher energy visible light while reflecting lower energy red and yellow wavelengths. Classical electrodynamics and standard Schrödinger equations completely fail to account for this optical divergence. The missing variable required to explain heavy matter isn't found in classical chemistry. It is the finite speed of light. To understand why gold looks this way, we must trace a physical chain of events that starts with subatomic special relativity and ends with macroscopic optics. The characteristic yellow of this metal exists purely as a macroscopic failure of non-relativistic physics. That chain begins deep inside the gold atom, inside the extreme electrostatic potential well of its highly charged nucleus, which contains 79 protons. A massive positive charge pulls inward on the surrounding negative electrons. Using a basic heuristic, an inner electron orbiting a nucleus with an atomic number of 79 must travel at roughly 58% of the speed of light to maintain a stable state. This chart maps atomic number against the Lorentz factor, the multiplier for relativistic mass. For light elements, the line is flat, but as we reach the heavy transition metals, the required velocity climbs, and the electron's relativistic inertia exponentially increases. At z equals 79, the Lorentz factor hits 1.22, meaning a 22% mass increase. We must correct a misconception here. The outermost valence electrons, responsible for metallic conduction and color,
are not literal moons tracing planetary orbits at 58% of the speed of light. Instead, we must look at quantum penetration. In quantum mechanics, certain electron wave functions, specifically spherical s orbitals, possess a non-zero probability density directly at the nucleus. Because the outermost 6s valence electron occasionally occupies this space, it penetrates the deep atomic core. By sampling that intense electrostatic well, the valence electron is subjected to identical high-velocity kinematics. These penetrating electrons are drawn into an extreme relativistic environment, forcing a strict modification to their kinetic energy balance to maintain stability. This kinetic disruption triggers a strict cascade of structural changes, moving from the nucleus outward. The first node in this sequence is driven by relativistic kinematics. Through the mathematics of the bright Pauli Hamiltonian, the relativistic mass increase dictates a negative correction to the kinetic energy. High-momentum electrons diving into the core lose energy. Because the defining equation for an orbital size places electron mass in the denominator, a 22% mass increase forces the radius to shrink. This is the direct relativistic effect. The outermost 6s valence shell physically contracts inward. It moves into a region of stronger electrostatic attraction, dropping its energy level and rendering the electron tightly bound, a process known as relativistic stabilization. To satisfy the Pauli exclusion principle and maintain quantum orthogonality, the contraction of the inner 1s shell forces the 2s shell to contract, which forces the 3s shell to contract, cascading all the way out to the 6s boundary. The absolute speed limit of the universe forces the geometric boundary of the gold atom to collapse inward, lowering its baseline energy architecture. We must also account for the other electrons in the valence structure, specifically the densely packed 5d orbitals lying just beneath the 6s shell. Unlike the spherical s orbitals, d orbitals carry high angular momentum. This creates a centrifugal barrier that prevents them from penetrating the deep nuclear core. They do not experience the direct mass velocity shift. However, because the inner s and p shells have now contracted, their electron clouds become intensely concentrated around the center. They form a highly effective electrostatic shield, masking the positive pull of the nucleus. Because of this dense barrier, the outer 5d electrons experience a drastically reduced effective nuclear charge. The inward pull they feel is heavily diluted. Loosened from the nucleus, the 5d orbitals are forced to expand outward radially. Their electrostatic binding energy decreases, pushing their energy levels significantly higher in a process termed relativistic destabilization. The relativistic collapse at the atomic core forces a reactionary expansion in the valence shell, lifting the 5d electrons out of their deep potential well. The orbital reshuffle is finalized by a third factor, derived from the Dirac equation, spin-orbit coupling. This is the magnetic interaction between an electron's intrinsic spin and its own orbital angular momentum. In light elements, this interaction is minor, but the incredibly steep potential gradients generated by heavy, highly charged nuclei massively amplify this coupling. The mathematical consequence is that the normally degenerate 5d energy states are violently fractured into two distinct energy levels, the 5d 3/2 and the 5d 5/2. When individual gold atoms condense into a solid crystal, this splitting physically broadens the overall 5d band, driving the highest occupied electron states even further up the energy ladder. Spin-orbit coupling acts as the final relativistic wedge, pushing the highest energy electrons dangerously close to the empty conduction band. As these modified atoms link together into a macroscopic, face-centered cubic metallic lattice, their discrete atomic orbitals overlap to form continuous energy bands. Without relativity, calculations predict the energy gap between the filled 5d band and the empty 6s states to be roughly 3.7 electron volts. This diagram shows the true energy architecture. Due to relativistic stabilization, empty 6s states drop down. Because of indirect shielding and spin-orbit splitting, filled 5d states rise up. The interband gap is crushed from both directions, narrowing to approximately 2.4 electron volts. In optics, an energy gap of 2.4 electron volts corresponds precisely to a photon wavelength of roughly 516 nanometers. That wavelength sits squarely in the blue and blue-violet region of the visible light spectrum. This establishes a new electrodynamic reality for the metal. Ordinary visible light now possesses the exact quantum of energy required to promote an electron across the gap. The subatomic relativistic reshuffle successfully translated into a specific optical vulnerability across the entire macroscopic crystal. When ambient white light, which contains an equal mixture of all visible wavelengths, strikes the surface of a gold object, the narrowed band structure filters the incoming photons. Low-energy photons in the red and yellow spectrum, which carry less than 2.4 electron volts, lack the power to excite the 5D electrons. Because they cannot trigger a transition, they are strongly and uniformly reflected by the free electrons on the surface. But the high-energy photons in the blue and violet spectrum carry enough power to cross the gap. When they strike the metal, they are annihilated. Their energy is entirely absorbed to drive the 5D electrons into the empty conduction band. Because the metallic lattice actively absorbs blue and violet light, the spectrum bouncing back to the observer is completely depleted of those higher frequencies. Through subtractive optical mixture, the human visual system processes this specific reflection as the rich, characteristic hue of yellow gold. If the universe were governed purely by non-relativistic mechanics, this optical phenomenon would be mathematically impossible. Gold would require deep ultraviolet light to trigger absorption, and to human eyes, it would look exactly like silver. By fusing the absolute kinematic speed limit of special relativity with the quantum mechanical architecture of the Dirac equation, we can accurately map physical reality. The sheen of a gold bar stands as a permanent macroscopic monument to the reality of relativistic quantum mechanics, sitting quietly in plain sight. In 1928, Paul Dirac successfully merged Einstein's special relativity with quantum mechanics, formulating an equation that accurately described electron behavior under extreme conditions. This animated diagram breaks the Dirac equation down into three distinct relativistic variables. We have the mass-velocity term, the Darwin term, and spin-orbit coupling. But in 1929, Dirac made a broad assertion. He argued that these relativistic corrections only mattered for high-speed subatomic particles and were irrelevant for ordinary atomic structure and chemistry. Dirac's assumption held for organic chemistry, where electrons travel at small fractions of the speed of light. Because the non-relativistic Schrödinger equation modeled these light elements with high precision, researchers focused on these systems, leaving the unique electronic architecture of heavy atoms largely unexamined until the late 1970s. The characteristic yellow hue of gold serves as a direct contradiction to this historical assumption. Under non-relativistic physics, gold should appear as a brilliant, featureless white. Theoretical elegance requires empirical proof. Resolving this contradiction between Dirac's mathematics and a solid gold bar would require a new approach, one driven by raw computational power rather than pencil and paper. The theoretical pushback actually started in 1935, when physicists like Bertha Swirls attempted the first relativistic treatments of many electron systems. Her equations were mathematically sound, but applying them to an atom with dozens of interacting electrons was practically impossible to solve by hand. The calculations were simply too complex. The breakthrough arrived in the 1970s. The hardware revolution produced early mainframes capable of delivering the brute processing power required to run these massive equations. Utilizing high-performance supercomputers, researchers like Pekka Pico, Jean-Paul Desclaux, and Kenneth Pitzer systematically modeled the heaviest elements at the bottom of the periodic table. By crunching the numbers, they proved that relativistic effects are not minor spectroscopic footnotes. They are the dominant forces dictating the chemical and physical reality of heavy matter. The physical origin of gold's color emerged from these early supercomputer simulations, identifying relativistic mass increase as the dominant force in heavy metals. To prove exactly why gold is yellow, we can use these computational tools to run a comparative simulation. We calculate the metallic band structure twice, once with the speed of light and once without it. First, we run the non-relativistic simulation. Here, the speed of light is treated mathematically as infinite, stripping away all of Einstein's kinematic limits. This diagram maps gold's non-relativistic band structure. Notice the massive 3.7 electron-volt gap separating the 5D band from the conduction band, pushing absorption deep into the ultraviolet. Visible light lacks the energy to cross this gap, so the metal uniformly reflects all wavelengths, appearing silvery white. We know empirically that gold is vividly yellow. The standard quantum mechanical prediction fails completely, exposing classical electrodynamic assumptions as mathematically incomplete. Now we pivot to the relativistic simulation. We enforce the exact speed of light, which acts as a strict cosmic limit for the electrons orbiting inside gold's heavy atomic core. The updated band structure reflects relativistic physics. A massive 79-proton nucleus forces the 6s orbital to geometrically contract and drop in energy.
This effectively screens the nucleus, forcing the outer 5D states to expand upwards. The interband gap squeezes violently from both directions, narrowing by 1.6 electron volts. The definitive calculation of this physical shift was published in 1971 by Niels Christensen and Bernard Serafin. This data point locks on to 2.38 electron volts on the narrowed band structure, matching the visible blue-green range. With this smaller gap, the metallic lattice absorbs high-energy blue and violet light. The reflected spectrum is depleted of these frequencies, heavily biased toward red and yellow. Today, theoretical physicists use advanced algorithms like the GW approximation and time-dependent density functional theory to plot these dielectric functions with even greater precision. While these modern computational tools refine the gap energies down to the millielectron volt, they entirely validate the causal chain established in 1971. The characteristic yellow hue of gold is the direct macroscopic output of narrowing a quantum band gap via the finite speed of light. To be completely rigorous, we must draw strict definitional boundaries around exactly which branch of physics is responsible for this phenomenon. This three-pillar logic model maps out our theoretical options: special relativity, general relativity, and quantum electrodynamics. The primary kinematic driver we just traced belongs entirely to special relativity, governed by fast-moving electrons inside a steep electrostatic field. General relativity plays zero role here. The macroscopic spacetime curvature generated by the mass of a single gold nucleus has absolutely no impact on the trajectories of its orbiting electrons. At the atomic scale, the gravitational force is roughly 10 to the minus 40 times weaker than the electromagnetic force. Gravity is mathematically irrelevant to atomic structure. We also have quantum electrodynamics, or QED. This field quantizes the electromagnetic vacuum itself, accounting for transient effects like vacuum polarization and the electron self-energy. While QED corrections are necessary to achieve milli-electron volt accuracy in modern theoretical modeling, they introduce only a microscopic destabilizing shift of roughly 25 thousandths of an electron volt. They are a refinement, not the macroscopic driver. The color of a gold ring is an exclusive everyday manifestation of special relativity interacting with quantum mechanics, completely independent of gravitation. Relativistic orbital contractions and expansions dictate the thermodynamic and chemical behaviors of the heaviest stable elements in the periodic table. Take mercury, sitting right next to gold at atomic number 80. The exact same relativistic orbital contraction pulls its 6s electrons in so tightly that they refuse to participate in the communal electron sea, drastically weakening the metal's bonds. Because those bonds are severely compromised, mercury lacks the lattice energy to remain solid and melts at negative 39 degrees Celsius. Its liquid state at room temperature is strictly dictated by relativistic kinematics. Move to lead at atomic number 82, and these high-speed kinematics drive the inert pair effect. This relativistic orbital stabilization is the invisible thermodynamic engine powering the chemical potential of the standard 12-volt lead-acid battery. From the sheen of a wedding ring to the liquid state of mercury, the extreme physics formulated to describe the subatomic limits of the cosmos also dictate the ordinary materials we hold in our hands. If the intense nuclear charge of 79 protons forces gold's inner electrons to move at relativistic speeds, causing orbital shifts that turn the metal yellow, it is logical to assume that any element with a massive nucleus would share that golden glow. But assuming that macroscopic color acts as a simple toggle switch for relativistic physics is a broad overgeneralization. An element's optical appearance relies on a specific intersection of forces. It depends on how relativistic orbital shifts interact with the element's unique band filling and structural matrix elements within a crystal lattice.
To verify exactly why gold looks the way it does, we have to look at its nearest neighbors on the periodic table. By seeing where the physical mechanisms diverge, we can isolate the exact variable responsible for gold's appearance. Special relativity is the engine driving the energy shifts, but the exact valence electron configuration acts as the steering wheel. Identically intense physical laws produce different optical realities depending on how those outer shells are arranged. This energy band diagram compares gold to silver. With an atomic number of only 47, silver's inner electrons do not reach highly relativistic speeds. This keeps its orbital structure intact, leaving a wide gap between its filled 4D band and empty conduction states. Since crossing that gap requires ultraviolet radiation, incoming red, green, and blue photons lack the energy to be absorbed. The silver lattice reflects the entire visible spectrum, rendering it a brilliant white. Copper, sitting directly above silver at atomic number 29, exhibits a reddish-orange hue, yet its low atomic mass guarantees that relativistic mass increase plays almost no role in its electron dynamics. The mechanism for copper is different. Its 3D shell is the first D shell to be filled in the periodic table, meaning it lacks deep core shielding from underlying layers. This lack of shielding leaves the 3D band pushed high and close to the conduction level, allowing it to absorb blue and green visible light through standard quantum mechanics alone. Neither silver nor copper relies on the extreme speed of light to dictate their visual appearance. Gold sits in that column as a unique outlier. With 78 protons, platinum has just one fewer than gold. Its inner electrons travel at virtually the same relativistic velocities, triggering massive orbital shifts. Yet, as we can clearly see, pure platinum is completely silvery white. We can identify the discrepancy by looking at this band structure diagram for platinum. With a valence configuration of 5d9 6s1, platinum is missing one electron in its 5d band. Notice how the Fermi level, the dividing line between occupied and empty states, slices directly through the middle of that band. This creates a high density of unoccupied states, exactly at the Fermi level. Platinum's electrons can instantly absorb and re-emit incoming photons of nearly any visible frequency via rapid intraband transitions. Cesium, at atomic number 55, can also appear pale gold, but classical electrodynamics, rather than relativistic interband absorption, drives this effect. As a heavy alkali metal, cesium has a large atomic volume and a low density of free electrons. This drops its classical Drude plasma frequency far enough into the visible spectrum that it begins to absorb violet and blue light. A heavy relativistic architecture does not guarantee a golden color. Gold requires the exact intersection of relativistic mechanics paired with a completely full D shell. If we move one position to the right of gold, adding a single proton, we reach mercury at atomic number 80. Here, the optical effects fade, and relativity dictates the metal's physical phase. Mercury features a full 6s2 valence shell. Driven by the 80-proton nucleus, these outer electrons experience an extreme relativistic contraction, pulling tightly to the core. Because they are locked down, they refuse to delocalize and share electrons when multiple atoms approach. Unable to form the robust communal electron sea necessary for metallic bonding, mercury atoms interact only through weak van der Waals forces, behaving more like noble gases than solid metals. Removing relativistic constraints to restore classical electron speeds, models show mercury forming a rigid lattice that melts at 400 degrees Celsius. A puddle of liquid mercury at room temperature is a macroscopic thermodynamic manifestation of special relativity. Moving 2 spots further right brings us to lead, at atomic number 82. Lead is another element defined by relativistic kinematics. Lead exhibits a phenomenon known as the inert pair effect. As this orbital diagram shows, lead's two 6s2 electrons are so relativistically contracted that they become chemically useless. Only the 2 outer 6p electrons remain available for typical chemical bonding. Restricting available valence electrons shifts lead's chemistry to favor the Pb2 oxidation state over Pb4, creating the thermodynamic difference between lead compounds that we need. That thermodynamic difference dictates macroscopic engineering. It provides the exact chemical potential required to generate electrical current in a standard 12-volt lead-acid car battery. Rigorous calculations demonstrate that if the speed of light were infinite, eliminating these orbital contractions, a standard lead-acid cell would lose nearly 80. According to standard electrostatic rules, these closed shells should repel each other, yet gold complexes reliably clump together to form stable structures. This diagram illustrates orbital. When the inner s orbitals of a gold atom contract, they screen the nucleus, forcing the outer 5d orbitals to radially expand. This indirect expansion scales the electron correlation effects between neighboring atoms, allowing them to draw together. The overlapping 5d orbitals form strong bonds at distances shorter than classical physics predicts. This structural quirk dictates the precise geometry of gold nanoclusters and the efficiency of gold-based catalysts. Relativity reshapes heavy matter across thermodynamics, electrochemistry, and nanoscale bonding. Gold's color is just its most visible signature. To understand exactly how the speed of light translates into an optical color, we can trace the math through a single, unbroken chain of cause and effect. Step 1. 79 protons force gold's inner electrons to 58% the speed of light. Step 2. Governed by Dirac equations, this velocity causes a relativistic mass increase. Step 3. This mass contracts the 6s orbital, expanding the 5d orbital outward. This geometric deformation of the atom is the unavoidable mathematical consequence of an electron obeying special relativity while trapped in a strong Coulomb field. Step 4. The solid state. Billions of deformed gold atoms form a crystal, squeezing the 5d and 6s energy gap to 2.4 electron volts. Step 5. Interband absorption. Striking white light hits this gap, matching blue and violet photons, which trigger transitions and are absorbed. The light that successfully bounces off the free electrons and returns to the observer is therefore entirely depleted of its blue and violet spectrum. The human visual system processes this specific subtractive mixture of reflected red, orange, and yellow wavelengths as a rich, warm hue. Gold's color is not due to classical optics, nor from standard quantum mechanics, and it has nothing to do with gravitational relativity or spacetime curvature. A gold ring is a tangible, room-temperature manifestation of special relativity. It proves that the high-energy laws governing the cosmos are not confined to the vacuum of space, but are locked within the ordinary materials we hold in our hands.